All right, welcome to this explainer. Today we're going to uncover the incredibly hardworking, mostly hidden mechanics that somehow make a violent, heavily potholed road feel like a perfectly smooth ride. I mean, if you've ever stopped to wonder how you can casually sip your morning coffee while hurtling down the highway at 70 miles per hour, well, you are definitely in the right place. Let's get into it. So picture this core physics problem. What actually keeps a 4,000-pound machine from just literally bouncing right off the pavement? If you completely removed the suspension system, every single time your tires hit a bump, they'd launch into the air and gravity would violently slam them back down. It wouldn't just spill your coffee, it would be incredibly seriously dangerous. Okay, let's dive into this roadmap. We're covering 1. The physics of the ride. 2. Springs, dampers, and sway bars. 3. MacPherson versus double-wishbone. 4. Geometry of alignment. 5. Magnetic ride control. And 6. Spotting a failure.
Section 1. The physics of the ride, managing vertical acceleration. Basically, a car's suspension has two totally contradictory jobs: maximize tire friction for safety while totally isolating you from the violent upward energy of the road.
To really grasp how engineers pull this off, we've got to break down two absolutely critical terms here: sprung mass and unsprung mass. The sprung mass is basically the weight of everything sitting on top of the springs: the chassis, the engine, and, well, you. The unsprung mass is the weight of the components between the road and those springs, so things like your wheels and axles. Think about a loosely sprung luxury land yacht. It easily swallows bumps to protect that sprung mass, but it suffers from some pretty severe body roll. On the flip side, tightly sprung sports cars aggressively minimize body motion for cornering, but man, they are way less forgiving on your spine. Moving on to Section 2, springs, dampers, and sway bars, the mechanical heroes. This is the actual physical hardware, managing all that crazy kinetic energy on your daily drive. The very first line of defense is the spring, which literally absorbs the bulk of the road's energy. We generally see 4 main types out there in the wild. Coil springs are the most common in modern cars, just heavy-duty twisted wire. Leaf springs are layered metal sheets, which you'll usually see doing the heavy lifting in trucks. Torsion bars utilize the twisting properties of a steel rod. And finally, air springs, which use compressed air chambers. And here's a pretty mind-blowing fact: both leaf springs and air springs actually date all the way back to horse-drawn carriages. Yeah, early air springs were literally just air-filled leather diaphragms acting like bellows on buggies. But here's the catch: a spring all on its own is actually a massive problem. Enter the shock absorber, or damper. Without this highly velocity-sensitive cylinder, the energy stored in your springs would just keep your car bouncing up and down. You'd essentially be driving a 4,000-pound pogo stick. Shock absorbers take all that bouncing kinetic energy and ingeniously turn it into heat by forcing hydraulic fluid through these tiny internal valves. And the faster the suspension moves, the more resistance the shock actually provides. Then we have the sway bar, sometimes called an anti-roll bar. When you take a hard corner, the body of your car naturally wants to lean outward, right? That's just lateral force at work. This surprisingly simple metal rod acts as an equalizer. It spans the axle connecting the opposite wheels. When the outside wheel compresses and the inside wheel tries to lift off the ground, the sway bar actually pulls that lifting wheel back down. It keeps the vehicle flat and maintains your cornering grip. It's a remarkably elegant solution. All right, Section 3, MacPherson versus double-wishbone, the heavyweight fight. Two incredibly common designs solving the exact same problem in very, very different ways. In one corner, we have the MacPherson struts, brought to life by Chevrolet engineer Earl MacPherson way back in the 1940s. It combines the shock and the spring into one single unit that also doubles as a structural steering pivot. It is incredibly simple, beautifully lightweight, and saves a ton of space into the hood, which is exactly why it's the standard for so many cars today. But in the other corner, we have the double-wishbone. This setup uses 2 A-shaped arms to independently guide the wheel. Now, it's definitely more complex, but it's shorter and offers vastly superior control over the tire's camber angle during suspension travel. That's exactly why low-slung, track-ready sports cars swear by the relentless grip of a double-wishbone setup. Now, what's really interesting about this next part? Section 4. The geometry of alignment, finding the perfect angle. This is the invisible math that dictates exactly how your car handles. We're talking fractions of a degree, literally determining whether you feel locked to the asphalt or totally out of control. First up is camber. That's the vertical tilt of the tire when you're looking at it head-on. Negative camber means the top of the tire tilts slightly inward.
Fun fact, Formula One cars dial in intense negative camber because when that car leans into a brutal turn, it flattens the tire out, giving them the absolute maximum contact patch for grip. Next is caster, the vertical angle of your steering axis. Positive caster is the magic that automatically returns your steering wheel to center after a turn and keeps you tracking dead straight down the highway. And finally, toe. This is the inward or outward angle of the tire when viewed from above. Dialing in a little toe in can stabilize a car at high speeds and reduce oversteer, whereas a little toe out helps reduce understeer so you get much quicker turn-in response. Moving to Section 5, the magic of magnetic ride, high-tech suspension. This is where we cross over from pure mechanical hardware into the world of modern electronics. You'll see this heavily in modern GM and Ford vehicles. Instead of standard hydraulic oil, these special shocks are filled with magnetorheological fluid. Wheel and body sensors are constantly, furiously reading the road surface. When you brake hard or dive into a corner, the suspension module zaps an electrical current directly into the shock. In a literal split second, that magnetic fluid thickens instantly. It transforms a plush, soft highway cruiser into a stiff, hyper-responsive sports car in mere milliseconds. It is absolutely wild technology. Finally, Section 6, spotting a failing suspension when the system breaks down. Let's make this super practical so you can actually diagnose your own ride. The absolutely crucial point here is knowing what to look for before things get dangerous. The first visual casualties are usually fluid leaks and really specific tire wear. If you peek behind your wheel and see a shock body that's all wet with oil, well, its vital hydraulic fluid has leaked out. Once that happens, your damping effect is totally gone. Your high-tech system just reverts to being a bouncy mass on a spring. And because the damper isn't absorbing the impacts anymore, your tire has to take the beating. This results in something called cupping, basically worn flat spots or weird ridges all along the outside of your tire tread. Now, if you ignore those early warning signs, you are going to experience some pretty severe symptoms. You'll feel the nose of the car diving hard toward the pavement when you hit the brakes, or the rear squatting backward when you hit the gas. The car might violently pull to one side, but the absolute worst-case scenario is bottoming out. That's when the suspension just gives up and can no longer support the weight, causing your chassis to literally slam into the road over standard bumps. It is a massive safety hazard, and it puts expensive bits, like your oil pan and transmission, at serious risk of destruction. And that brings us to the end of our explainer. But I want to leave you with a quick, real-world test you can go do right now. Next time you park your car, safely but firmly push down hard on one corner of your bumper, and then just let go. Does the car return to its resting position and settle instantly, or does it bounce up and down a few times like a trampoline? If it's bouncing, well, it might just be time to take a much closer look at your mechanical heroes. Thanks for joining me to uncover the hidden, totally fascinating physics of your daily commute.